So the question is, you have these maps.
Are you sharing the screen with us, Doc?
Yeah, can you see now?
Yes, we can now.
Okay. So and we have the disjoint union. This is the inclusion map, and similarly over here. Sorry, it is A plus B C plus B. Okay. So this is the initial diagram. Now remember a property of this. So recall in fact this is a characteristic property. I'll say it Y. So we have defined A plus B as, if you remember, this is A cross 1 union B cross 2. And this is iota B takes a member to the pair. So this is actually a set of pairs. So second coordinates are either 1 or 2. The 2 comes for the members from B and 1 comes for the members of A. So iota A is taking A to A1. Now the characteristic property is, suppose you give me any set. So given any two functions Fa and Fb, there exists a unique function F such that F composed iota A is Fa and F composed iota B is Fb. So remember this, right? And how did you define this function? Well, Fx is equal to Fa of say A if x looks like this, and this is Fb of B if x is looking like this. Okay? So explicitly we constructed this set A plus B, and we know that it has this characteristic property. So now let's see. So what's the picture? The picture is you have this thing. Whenever you have this triangle kind of a thing, there is a unique way to fill up this. So now you see, you have to recognize this triangle. You see, this gives me one map. And this gives me the other map. So now you are perfectly, so this part is iota B composed F. And this part is iota D composed G. So now you are exactly in this scenario. You have a set and two maps, one from A and another from B, coming to that set. So this says, by the characteristic property, this says that there exists therefore a unique map H, such that H composed iota A is iota B composed F, and H composed iota B is equal to iota D composed G. So now if you erase this part, what you still get is then, so what you still get is, so this is the erased part, so you get that unique, and that's diagram 55. You get that unique map, which makes the left hand and the right hand squares to commute. And obviously, if you want now explicit description, you know what this description would look like. Because A plus B consists of only points like this, there are only two types of points, A1 and B2. So where is A1 coming from? It's coming from A. And what is H of A1 therefore? H of A1, it is this, so it is going to be same as this. So first you take F and then this, so this is F of A1, and H of B2, by the same technique, it is G of B2. So that's the description, explicit description of H. Whereas this is the proof. Is it clear?
Yes, it is.
Okay.
It is now.
Okay. Now let me say, yes. You had something more to say?
No?
Okay.
No, I'm comfortable now.
Okay. Now let me show what I did not show earlier. Trying to validate this part. So what do I mean by characteristic property? I mean to say that the disjoint union, or A plus B, is a set which has this property. What is the property? The property is that the disjoint union is now characteristic property of the disjoint union. So what is the property that I have stated? It looks like this. So there are two maps along with this. Whenever there are two other maps from these endpoints, there is a unique way to fill this up. So let me rephrase this. So what is the property? And what is the property of? The property is of triples. Say S uh, of triples, let me write this as, say, I don't want to use, so let me write, say, IA and IB. Where? What is that? So, what is IA and IB? S is a set, IA is a function from A to S, and IB is a function, is of triples. And what is the property? That if you have another such map, if you have another such triple, so you have another such triple like this, right? Then there exists a unique function h from S to T. Such that H composed IA is JA and H composed IB is JB. Now what do I mean by it is the characteristic. So we have shown one, that the triple A plus B, that is joint union, and the coproduct injections iota A, iota B have this property. We have shown that, right? Now here is the second one. If S IA have this property, have the property, then there exists a bijection, a unique bijection, not only a bijection but a unique bijection H from A plus B to S, such that H iota A is IA and H iota B is IB. Now let's see why. So I have that this one already has such property, which I am drawing, and you have told me that this one, this triple also has this property. Now, since I have two functions coming from A, right, into S, and A, this triple on the top has this property, so I have this unique map. So H iota A is IA and H iota B is IB. Again, now just tilt this picture. You have this triple again over here, this one, as I am drawing, this A to S and B to S. So this ASB, this triple also has this property, as you have told me. And you have these two maps, iota A and iota B. So by the property that S possesses, you are going to have a unique map P such that PIA is iota A and PIB is iota B. Now let us do some calculations. So it's similar what we did last time. So let's do some calculations. So H iota A is IA. So PH iota A, this is PIA, but this is iota A. And similarly, PH iota B is PIB is equal to iota B. Now observe, we have this scenario. Now, you told me that if you have any thing and two maps, there is a unique map. So I take A plus B in particular. So I have these maps. And therefore, since you told me there is only one way to come from top A plus B to this one, can you give me that one obvious way? It must be the identity map. Because there is always this identity map which makes these two triangles to commute, and if that is the one, then that must be the unique one, because you told me there always exists one and only such map which makes this diagram to commute. So this is equal to nothing else but identity of, and this is equal to the same thing. Now look into this part, this and this. You have two things, PH and 1A plus B. PH and 1A plus B. So this, from this uniqueness, therefore implies that PH is 1A plus B. And the same story again, because this triplet also has this triplet has this property which says that whenever you have any such thing, then there is a unique way to come from here. So if you did take S also over here, then the identity of S would be that. So therefore, similarly, HP is identity of S. So what do I have? So I proved, therefore, so this, all this calculation tells me that PH is identity of A plus B and HP is identity of S. So one must be the inverse of the other. So it means that P must be H inverse. So H is a bijection and P is its inverse. So I did not remember P also. So remembering H is a bijection. So it's a unique bijection by this, as I have told you, satisfying this condition. So what is the characteristic about? So you cannot have any other such triplet other than the disjoint sum and the coproduct injections. So you see, it's characteristic, I need not know. So you see again over here what I am doing is, although I constructed this A plus B quite explicitly, and as well as these maps also quite explicitly, this is something over here which tells us another way of thinking of A plus B. But the only problem is that we cannot think of A plus B isolated. We must think it as a triplet now with these two coproduct injections. So this and this triplet therefore has this characteristic property as this. Is this not nice? You see, this is an alternative way to think of. You never need to look inside what is it there in that set, but up to a bijection you can completely determine that set. Okay, up to a bijection, up to a and if you are happy with that, it depends on what kind of state of mind you have. If you are happy with that, well, then that is it. So you see, this is a characteristic property. So is this clear? Yeah?
Yeah, it is, Doc, it is clear.
Good. So, any more questions? Or where did we stop? Last time I don't remember. Where did we stop?
With this something, Doc.
With these factorizations, right?
Yes.
Okay. So any questions? Any more questions? Any questions?
I'm okay, not from me.
Okay. Any others? Okay. So now, as I say, yeah. So, yeah, did somebody want to say something? No. So, now, as I said, so every function factors as a surjection followed by an injection. And such factorization we have seen is unique up to isomorphism, up to a unique isomorphism. And one such explicit such is where you take I to be the range of F range of, I forget what symbols I have used before. So range of F, you take I to be the range of F, which is precisely the set of Y in B such that there exists an X in A such that Y is equal to Fx, or in other words, this is just Fx as you make your X vary over A. And your M is the inclusion map, which takes this Y to Y itself, and your E is, well, I wrote it as F sur something like this, Fs, I wrote it as fs, which takes an x to fx. So although your map E in this special choice has the same formula within quotes as f, it is not the same function because the domain of E and f are not the same. Okay, I mean to say the codomain is not the same, and property wise you can see that they are different. So as a consequence of this, I said that every function therefore is kind of a mixture, and obviously it is a mixture. I'll still use the word mixture, but as you know, mixtures, even if they are not chemical, you know, you have a difference between a compound and a mixture. Compound is something else. I don't know whether we should use the same terminology. It's a mixture, so in part it has properties of injection, and in part it has properties of surjection. So, and this part business plays a big, how much, how big, and so on, and that's where all the beauty comes in. Now, so it's enough to look into these specific types of maps separately, and that's what we will start today. Now firstly, so we look into injective maps, injections. So firstly, as I said in one of the examples on the tables, you remember this factorization, as I said, is unique up to a unique isomorphism. So your M was in that special case, but what it says therefore, that M being an injection is essentially like a subset. It may not be a subset, but it is like a subset. You can get this feeling, right? Therefore, and that's why I made this comment that, well, injections are essentially subsets or inclusion maps. So, because any other inclusion map, any other injection is actually a copy. In what sense? So let us try to draw a picture. So what is an inclusion map looking like? Here is the set A, and here is a subset P. So you have this inclusion map. Now why I say, well, if you have another set and there is a bijection between this set and P. Okay? So you have a bijection here, right? So this bijection defines a, so I'm saying the way that I have drawn, this defines an injective map into A. Clear? This one composed with this is obviously the injection. So that means there is a bijection. So that is the idea behind saying that any injection is actually up to a unique isomorphism, so more formally, so suppose if you had M to be an injection, then you take this injection, and if MS is going to P with, so there is a bijection over here, which is, so that's what I'm saying as I drew in this picture. Now, who told me that this is the only thing? Well, I could have another set also over here in bijective correspondence with this. So you see there are, so let's take a concrete example. So let us take this set A, say the set of the first 10 natural numbers, and let me take P, say 2, 7, 9, 5. So this is a 4 elements. So obviously you have this IP very much there. But remember, you have several other, so you could have a set like this, which is 2, 4, 6, 8. You could have a set like this, A, B, 2, 4. Or you could have a set like this. Right? All these sets are in bijective correspondence. And you can see, therefore, all these sets are in bijective correspondence, and all of them, therefore, define an injective map into A. Okay? So the picture, so going away from specifics, is the moment we now go away from specifics, we see that there are several bijective, there are several sets. They are in bijective correspondence. So I am writing it like this, of which one is a proper subset possibly, and composing with these bijections, you have all of these to be injective maps from here. Okay? So you see the picture is like this, that you have several sets from where you have an injective map, and however there is you can find from all these things, thankfully, using our set theory, we can find one of them which is actually a proper subset, and one of which is this inclusion map. But there are several other injections into it. So this is the real life story. Now, therefore, we can take P as a representative of all these P primes, P double primes, and so on. It's just a representation. The only difference is that this representation, this is where you can say this is the boon of explicitness, that we have this P as exactly sitting inside A. Okay? Nothing more than that, though. Now let's see about comparison. So if we have, so let's start off with the same idea. So what is a comparison? So if you have another subset, well, if you wanted to take another subset Q, So you mean to say that Q is bigger than. So therefore, for that Q, you are going to have a similar picture, right? You are going to have a similar such whole list of things. So let me try and draw a few. So you have a Q, similarly you have a Q prime, Q double prime, and so on. And now I have to be careful. So this is your IQ, this is your other inclusions that you similarly have, all coming towards A. And these are again, as you said, bijections. And likewise for all possible subsets that you might think of. Now, how do you rephrase this fact that P is a subset of Q in terms of these maps? Well, since P is automatically a subset of Q, you have the inclusion map of P into Q. So you actually have a map here. And the inclusion map, so inclusion map, see, what we are saying is inclusion of map of P into Q followed by the inclusion of Q into A is nothing else but the inclusion of P into A. So you are telling me that IP is nothing else but IQ composed I. Okay? So here is a nice way, and this composition is actually telling us something. It is telling us this smallness. So let's see. So given this, we are not given this diagram, this scheme. So we will now loosely think of pairs like M and M, where is an injection as a representative of a subset of A. And how will you compare? So if we have comparison, so we will say that, well, M is smaller than N. So we will say that M is smaller than NN, or even we will say NN. So alternatively we will also say NN is bigger than MM. We'll in fact write this as now observe, as you know, a function is determined by three things: its domain, codomain, and its rule. So, well, M doesn't, because there can be several one-to-one maps coming from here to here. M doesn't. But M, the small m obviously. So we can as well shorten our symbol over here instead of using pairs, we can use symbols like this. Okay? So we are kind of, I'm saying, we can shorten. So when will we say all such things? As we just noted, remember this one. P was smaller when from the small to big you have a map. So you have a morphism. So you have a function h. So this means, that is, when there exists a function h from m to n such that, so nh is equal to m. Okay? Now observe. Note. This h is unique. Why? Suppose if you had another such. So if m is equal to nh and is equal to nh prime. Now you know n is an injection, so it is cancelable from the left. Then h is equal to h prime, left cancellation. Okay? So this h is unique. Secondly, this h is injective. Remember we said, so m is equal to nh. Remember we said that if a composite of two functions is an injection, then the right hand one, so this h becomes an injection. So that says, so remember, recall, or let me refer to that proposition which was there, I think somewhere here. This is 5.12, I think, yes, 5.16c. And this is 5.12. Okay, so you see this h is an injection. So the original idea therefore prevails even in this inexplicit and this way of stating that you see here we also said that P is a subset of Q. Okay, so the same thing also prevails over here. So now let us see how much can we go with this way of describing things. So we have all these. So now it's not that same old scheme that I'm saying. Now I'm drawing. So suppose if m, I have taken an m. So number 3, there is always this one is the largest. You see, mm is always smaller than a and identity of a. So the identity of a, that gives us the largest such thing. Why? Well, there is only one way you can do it. There's only one way you can do it. Okay? Alright? This is obviously implies yeah, So, is someone missing? Stanley. So why? So here we have it. We had this M, we had this N, and we have this P. You told me this is there, so you have a map here. You told me this, so you have a map here. But then there is the composite map. So that gives me this. You see, the definition was too loose. It said if you just wanted to bridge this, okay, if you could do this, then this is the smaller one, the tail is the smaller and the head is the larger, right? So that was the whole thing about. And see, now it becomes clear that this is also, so what are you saying over here? You're saying that, well, everything is a subset of A. That's what you're saying. This is saying M is a subset of N and N is a subset of P, so M is a subset of P. So transitivity. Now comes the real story. In this way, we somehow cannot capture the equality. And let's see where it fails. So suppose if we have this. So the picture is this. So there exists an H and there exists a P. So M is equal to NH and N is equal to MP. So therefore M is equal to NH, which is again equal to MPH. But then M is left cancelable, so this tells me that pH is identity of M. And similarly, N is equal to MP, which is equal to N of HP, which tells me HP is equal to identity of N. So, P and H are in bijective are bijections. One is the inverse of the other. So, in this case, what happens is, so this implies that there exists a bijection such that so you're exactly in this situation, this one. So you're in this level. So yes, all of them are essentially the same, and the level of P's are less than the level of Q's. So each one of them, you can see, this is smaller than this is smaller than this. Okay. Now the question is that our expectation was, with being explicit, our expectation had become too much restrictive. What was the whole story about equality about? Well, the whole story was if A is a subset of B and B is a subset of A, then A is equal to B as sets. That was my definition of equality, and that's why we had the equality there. And that's the case. And how do we know that? Well, we explicitly calculate for each object whether that object is an element of the set A or not. And that's how, to be specific, it's not any calculation, it is exact verification. You take up an object and you check whether this is a member of A or not. Well, if it is, then you check whether it is a member of B or not. Okay, and so you go on checking. So it's a kind of an infinite table that you are making. So for each element of A, if you have a check for B and vice versa, then you say that. So you are doing, to do this explicitly, you are actually making an infinite check at every stage. On the other hand, here we cannot do that checking. We are not checking anything at all. We are just moving by this composition kind of a thing, and we cannot expect to make a checking. What we can expect is something like this, is a bijection. We will have to be satisfied with this much. But the real case for us is that this is it. Why? We are going to see that we don't need to do the explicit checking. We just need a few comparisons. We don't need further explicit checking. So now let's put forward some specific comparisons. So some specific comparisons. The first, the power set. So we will, as we said, that we will say, where is it? Yes. We will either say this, or sometimes it is more customary to even say this. Okay? But, okay, you know the power set of any set is larger than the set. So that means I am going to produce. So how does the proof go? The proof is quite interesting. So here are a few proofs. Some of the ones I said I'll do, although you have to recount them, prove it again. But this is a classical proof. So how does it say? So take a set A. Take a set A. And so suppose obviously obviously you have this function, obviously. Why do I do that? There is this function. F from A to, how did I denote the power set? Was it 2 to the power A? Did I say that? Or did I use this symbol? Whichever. So what do? I take X and I go to the set which contains the single point set X. Okay. So obviously there is this function, and clearly F is injective. Okay, so F is injective. The whole point of the set, so it is bigger. Now, is it possible that there is a bijection between this? So bijection means it must be injective and surjective, but I say something more. So if possible, let be a surjection. So it means that every element of this has a pre-image. And take any element from here, which is the same as saying that T is a subset of A. Okay? Now let me construct this set. As G is a surjection, there exists X in A such that Gx is equal to T. Okay. So this is the meaning of saying that it is a surjection. So I should say that this is what I meant by. So this is just a. Okay. So now you have assumed that G is a surjection. Okay. Now look into this set. S is the set of all X in A such that when you look into the set Gx, remember Gx is a subset of A. You are saying that X doesn't belong to it. I don't know whether S is a empty set or S is the whole of A. I don't know. So now, this being a subset of A, there exists a Y in A such that G of Y is equal to S. That's what you have told me. But then, can Y belong to S? Suppose Y is a member of S. Then Y must satisfy its defining condition. But what is GY? GY is nothing else than S. So, which is a contradiction. And where did this contradiction come from? It came from the fact that for this subset you can choose a pre-image. And this came from the fact that because you assumed that this is a surjection. So hence, there cannot exist a surjection from A to 2 to the power. Therefore, 2 to the power A is larger and strictly larger and strictly so than. So that's the proof. Okay, so you now have, starting with this, so it tells you the power set of any set is strictly bigger than it. So now you see, you have started, so you have now this big chain. You have this, you have 2 to the power this, which is nothing else but 1. You have 2 to the power 1, which you know is nothing else but the 2 element set. You have 2 square, 2 to the power 2, which you know is the 4 element set, and so on. And it carries on and on and on. You take any set X, you have a set which is larger than that. You take that set X, you take that, take the power set of it, it is still larger. So this hierarchy never stops. Never ever stops. So this system is already giving you a huge collection. So you see. Now, sure. Yeah.
Oh, okay. Can we say the power set is infinite?
You cannot say the power set is infinite, because for instance, firstly, we didn't speak so far what is finite and what is infinite, but even if you boil down to your intuition, you can never call this power set of the empty set as infinite. What you are trying to say is the process of taking power sets is infinite. It produces bigger and bigger and bigger sets, right? You possibly wanted to say that. Yes, exactly, that is true. So, by taking power sets of power sets of power sets of power sets of power, and so on, you are getting bigger and bigger and bigger sets. That's true. And this process never stops. Never ever stops. So that's right. So therefore, you see, even with this minimum thing that we have taken, we can build this huge collection of entities. So now the next question is that how do we, this tells us that it produces some comparisons. It produces a way gives us a way to compare, but it doesn't tell us anything more than that. It doesn't tell us how do we decide. So the question is, how do we decide on having kind of saying same number or same number of elements or same size, or so on and so forth. And that is where, well, by the way, this proof is a classical proof, and this technique used over here is usually called the Cantor's diagonalization argument. It is similar. It is exactly similar, and strangely speaking, the motivation and inspiration of Cantor came from that simple proof that he gave of showing that the real numbers, there are uncountably many real numbers. It's essentially the same proof, the same principle. Okay, so that's why he utilized this, and people later called it Cantor's diagonal. So diagonalization argument. And now here it is another story. So this is called the cantor-schroder-bernstein theorem. So it says if A is smaller than B and B is smaller than A, then A and B are in bijective correspondence. So making it clearer, so you are telling me that is, if you have two maps, A is smaller than B, so F is, you have a map from A to B, which is injective, and you have a map from B to A. So if you have injective maps both ways, then there is a bijection. There exists a bijection. Okay? We will prove the Schroeder-Bernstein next time, next day. It's a little bit. I don't want to do both the proofs on the same day, and I think also an hour is over, so it could be tensed. But let's give a quick follow-up of what this gives. Well, what this gives? Well, so some applications. So, assuming n, the usual numbers and so on and so forth. So, first one, n. So, we will write and in bijective correspondence, and we will write it like this. And we will say that they are of the same size, or we will say equipotent is the more formal word. Equipotent. Potent is power, potency. Equipotent is. So n is equipotent to n cross n. It is equipotent to, therefore equipotent to, and so on. Where k is any. And how do you prove this? Well, the proof is, so you have to produce two injective maps. And how do you do that? Obviously, if you take Fn to be equal to n1, you are done, one side. What about the other side? You take 2 to the power m, 3 to the power n. And obviously, from the prime factorization that we know, this immediately says that G is injective. So Schroeder-Bernstein says they are equipotent. Done. You can never think of this in case, say, this is never true. So if you had A to be like this, and this is distinct, A cross A is never equipotent with A. Right? But here is something which is happening for N. So definitely you can start thinking that this set A that you did take is, well, or sets like this. So essentially sets like this are definitely not the same kind of sets like this, like N or others. Is there only one such? No. Here is another one. If N is equipotent to A and this is also equipotent to B, remember this therefore means that N is equivalent, then A is equipotent to A cross B. I'll leave this as a proof. Use the definition that this means that there is a bijection between them to translate this one that I did just now into this, to translate into a bijection between A and A cross B. So how does this help us in getting more? Here is it. Here is a whole list of things which is equipotent with N. N is equipotent with Z, Q, all surds, and what do I mean by this? That means how do I write this? So it looks like this. What is a surd? It is say m times root 3 plus n times root 5 and so on. Why only root? And so on. Well, let's and finite such expressions of this kind. This one would be a little more difficult, but let's see something more that you can do. Okay, all polynomials with in a single variable with coefficients from A which is equipotent with Z. So, all such polynomials that you can think of, okay, the set of all such. So, this is the set of all such polynomials, and usually this is denoted like this, okay. So, why do I make it a coefficients from Z, say? So usually this is denoted from this, by this. So how does it look like? It looks like P0 plus P1x plus p2x square plus pnx to the power n, and it stops, and these are p0, p1, etc. These are numbers from z. Okay, so all of them are like this. But so you might think that, well, is this everything? But your first one, this first proposition already tells you there are sets bigger than this. So there are sets bigger than this. So for instance, 2 to the power n, that is not equipotent with n. It is in fact bigger than n, as you know. But what is this? This is equipotent with the real line. So that's where we actually see the power of this cantor-schroder-bernstein theorem in showing that this is actually nothing else but subsets of R. And how does one do this? Well, so one has to give two functions from this side to this side. So what do I do? Well, I take a subset, say T of n. So let it be say T1, T2 and so on. And I take by F to this infinite sum. And I leave it to you to show that F is injective. Okay? The whole idea is here. You see, the whole idea is you have to come to terms with this. Remember, we showed that every real number has an infinite non-terminating decimal representation. Now, how do we calculate the decimal representation? If you take, instead of decimal means it's base 10, that means your digits are 0, 1, 2 up to 9. You can do the same thing with, instead of 10 you can take base 2. So every real number has a unique infinite binary representation. So that is the goal. That is exactly what this is doing. And what is GR? Well, this is this set. If R is so I write it like this. So that is exactly the whole idea behind this. So this tells you, so you see, and again the next stage, the proof is similar, but now you have to think. Here you use the prime factorization. Here you have to use something more. around these things. So, okay. C, the complex numbers, same as R. So you see now there are several, but you know that there is something bigger than that. Okay? This is bigger. And so on, this whole thing carries on. So you see this whole branch, this whole study, and you can see this classification in this way of sets in terms of sizes is just possible with the simple notion of injective function. So essentially it is a kind of a tool towards counting. Now counting, we will come back to it. What exactly is counting, we will come back to it when we speak about finite and so on and so forth. We will come back to it later on. Yeah, I'll stop today. Any questions, any clarifications and so on? I think Stanley was disconnected, so possibly he will see the video. Okay, any questions? Yeah?
On my side, not at the moment, Doc. I just have to go through this again, and then maybe I'll come up with something.
Yeah, okay.
So for now, no.
Okay. And Roselle and Ayub?
I'm also going to review the notes, Doctor, and then see if there's anything coming up, like Charles.
Okay. Okay, sure. I'm not having your weekly, I mean all of you, your weekly submissions. So remember, they are important. So because
Yes,
Yeah, no. Yeah, we are working on them, Doc. Very soon we'll submit.
okay, okay.
All right.
Roselle? Okay, I don't know whether Roselle has any question or not. Okay, in that case, if you don't have any, then we can meet again next time.
All right. Thank you very much, Doc. Good night.
Thank you, good night, keep well and safe.
Thank you, Doc.
Thank you.
Thank you, Dr. Bartha.
Thank you.
Good night.
Good night. Good night.